Imagine the human brain, a complex network of billions of neurons constantly firing and communicating. This biological marvel serves as the inspiration for artificial neural networks. These networks, like their biological counterparts, are designed to process information and learn from it. Just as our brains recognize patterns and make decisions, neural networks aim to replicate this process artificially. Neural networks are revolutionizing the way we interact with technology. From voice assistants like Siri and Alexa to self-driving cars, these powerful tools are changing our world. But how do they work? The key lies in understanding their fundamental building blocks. By mimicking the interconnected structure of the brain, neural networks can tackle complex tasks. They learn from data, identifying patterns and making predictions with increasing accuracy. This ability to learn and adapt makes them incredibly powerful tools in today's data-driven world. At the heart of every neural network lies a fundamental structure: layers of interconnected neurons. These layers act as processing units, working together to analyze and understand information. Imagine a neural network as a factory assembly line. Each layer represents a stage in the production process, with data flowing from one layer to the next. The first layer, known as the input layer, receives the initial information. This could be anything from pixels in an image to words in a sentence. Like workers receiving raw materials, the input layer takes in the raw data and passes it along. The middle layers, called hidden layers, are where the magic happens. Here, neurons process the information, looking for patterns and relationships. Within each hidden layer, neurons are interconnected. Each connection carries a weight, signifying the strength of the relationship between two neurons. Finally, the output layer delivers the network's decision or prediction. Like the finished product rolling off the assembly line, the output layer presents the results of the network's analysis. While the structure of layers and neurons provides the framework, activation functions breathe life into neural networks. These mathematical functions determine how a neuron responds to its inputs, essentially deciding whether a neuron should fire and pass on a signal. Think of activation functions as switches that determine whether a signal is strong enough to continue through the network. One commonly used activation function is the sigmoid function. It squashes a neuron's output to a range between 0 and 1. This allows the network to represent probabilities, making it useful for tasks like image classification. Another popular choice is the ReLU, or rectified linear unit function. ReLU introduces non-linearity into the network, enabling it to learn more complex patterns. Imagine a light switch that's either on or off. That's ReLU in action. The choice of activation function depends on the specific task and the characteristics of the data. By carefully selecting and combining activation functions, we can optimize neural networks for a wide range of applications. Section 4. A diverse family, exploring different neural network types. Just like there are different types of brains in the animal kingdom, there are various types of neural networks. Each type is tailored to excel in specific tasks, showcasing the versatility of this technology. Convolutional neural networks, or CNNs, are masters of image recognition. Inspired by the visual cortex of animals, CNNs use filters to detect patterns and features in images. Think of a CNN as an art critic, analyzing brush strokes and composition to understand a painting. Recurrent neural networks, or RNNs, are the language specialists. They have a unique ability to remember past information, making them ideal for processing sequential data like text and speech. Imagine an RNN as a storyteller, weaving together words in a sequence to create a narrative. These are just two examples of the diverse family of neural networks. Researchers are constantly developing new architectures and algorithms, pushing the boundaries of what these networks can achieve. Section 5. The power of neural networks, shaping our modern world. Neural networks are no longer a futuristic concept. They are interwoven into the fabric of our daily lives. They power the personalized recommendations we see on streaming platforms, allow us to translate languages instantly, and even assist doctors in diagnosing diseases. In the field of medicine, neural networks are analyzing medical images with remarkable accuracy, aiding in the early detection and treatment of diseases. They are also accelerating drug discovery, helping researchers develop new treatments at an unprecedented pace. As we generate ever-increasing amounts of data, neural networks will play a crucial role in making sense of it all. They will continue to shape the future of artificial intelligence, leading to innovations we can only begin to imagine. The journey into the world of neural networks is just beginning. As we continue to explore the vast potential of these powerful tools, we can expect even more transformative changes in the years to come. The future is intelligent, and it's powered by neural networks.